All right, Unit 9 is where we will start talking more about right triangles and trigonometry. But we'll start off with the Pythagorean theorem, section 9.1. And we know that this Greek mathematician had a prominent nose, which is where he got the idea for the famous theorem. All right, our objectives are to use the Pythagorean theorem and its converse and be able to classify triangles. And then our essential question, how can you prove the Pythagorean theorem? And if you'll take a note of the two images you see here, this is sort of an intro to an activity that we will do in order to help us answer that essential question. All right, so we know the famous Pythagorean theorem. It states, if you have a right triangle, then c squared equals a squared plus b squared. And then one thing that's new for us is our implied statements. It's always the shortened versions of the formal conditional. So our conditional is shortened down to right triangle implies c squared equals a squared plus b squared. Just remember that funny word hypotenuse is always across from the right angle. So find that right angle and then go across. There's your hypotenuse, always the longest side, and we usually label it C. Then the other two sides are known as the legs, and we label those A and B, and it doesn't matter which one is which. All right, so once we start doing the Pythagorean theorem with multiple situations, we start to discover some patterns. There are very common Pythagorean triples. Basically, these are sets of three numbers that we know as sides A, B, and C on the right triangle, and they satisfy the Pythagorean theorem. The bolded items on the top row of each list here are our common ones. So if you ever see a combination of these three sides, we know it's a right triangle. 5, 12, and 13 is another combination, 8, 15, 17, and 7, 24, and 25. So if you see any of these combinations, you can automatically conclude that it's a right triangle. And then what's under our bolded common triples is a list of multiples. So this next row is if you were to multiply that top row by 2. And then the third row is all multiplied by 3. So essentially, anytime you multiply your common triples by any factor, it's a Pythagorean triple. All right, so let's try the Pythagorean theorem and tell whether it is a Pythagorean triple. So we have lengths 5, 12, and we're trying to find the length of the hypotenuse. Start by writing out your Pythagorean theorem. So a squared plus b squared equals c squared. Then substitute your leg lengths. In this case, we've got a leg of length of 5 and a leg length of 12. So it doesn't matter which one you give as the a value and which one you give as the b value. So 5 squared and 12 squared. And then our unknown c value, the hypotenuse is always c, is labeled x, so we can substitute x squared. Then square your values, so you get 25 and 144 equals x squared. Combine like terms, get 169. So next you want to square root both sides. To undo x squared, you have to square root it. So these will cancel out. The x squareds and the square root undo each other, leaving you with a square root of 69, which is the positive and the negative value of 13. But the only value that works in this case is the positive 13 because it represents length. All right, since the value of x is 13, the side lengths 5, 12, and 13 are integers that satisfy the equation c squared equals a squared plus b squared. So it does form a Pythagorean triple. All right, now pause the video here to try it on your own. Example number 2, find the value of x, then tell whether the side lengths form a Pythagorean triple. All right, see how you did? Did you get x equals 7 times the square root of 3? Since this value is not an integer, the side lengths do not form a Pythagorean triple. And let's take a note here, a moment to take a note here of the way that the value is simplified. I will be expecting you to simplify radicals to its exact value. And the easy part is to type it in and get the approximate value on a calculator. So make sure you know how to simplify your radicals, which is why I gave you an extra page to practice and review the skills of simplifying radicals. And at the end of this video, I will also go over the skills of simplifying radicals if you need a refresher. All right, let's take a look at this real-world application of Pythagorean theorem. We have the skyscrapers shown are connected by a skywalk with support beams. So here's our two skyscrapers, and then here's the skywalk. Use the Pythagorean theorem to approximate the length of each support beam. So as you can see, we have right triangles, this leg and this leg with the beam, so the side of the building with the horizontal beam here create the right angle, and then the support beam is your hypotenuse. So each support beam being the hypotenuse, you would plug in the values that are given, so we know that one of the legs is 23.26 length, and then we know that the other leg is 47.57 length, as indicated by our two markings. So we substitute n to a squared and b squared, and you will definitely need a calculator to square these values. And then to undo the squared, you would square root both sides. And we have the positive and negative values when you square root, but obviously the negative value gets eliminated. And so we're only dealing with the positive value to have positive length. So the length of each support beam is about 52.95 meters. And I do want you rounding all values to 3 decimal places. So this is actually 52.952 meters. All right, this is an extra example involving a 25-foot ladder that rests against the side of a house. The base of the ladder is 6 feet away. Approximately how high off the ground is the top of the ladder? Round your answer to the nearest tenth. So I've started you off with an image. So sketch this situation and try this one on your own. All right, did you get an approximate height of 24.3 feet? If not, check my steps and see if you can identify your error. If not, bring in your questions to class tomorrow. All right, next we have the converse of the Pythagorean theorem. And remember, converse is switch the hypothesis conclusion. So now we're saying that if c squared equals a squared plus b squared, then you have a right triangle. Shortened down to our implied statement. Please make a note, c is always the largest side. All right, let's take a look at example for part A. Here we have our 3 side lengths. We can see that the hypotenuse appears to be the square root of 13, and the square root of 13 is approximately 10.630. All right, so plug in all your values to see if this is indeed a right triangle or not. Okay, so after you plug in all your side lengths into the appropriate locations of the formula, you discover that 113 does equal 113, so it's balanced on both sides. I didn't move anything around. I just kept everything on their designated sides of the equal sign, and then just waited until the very last step to decide whether this triangle is a right triangle. And when I have equal values on both sides of the equal sign of the equation, then we can conclude that it is a right triangle. And real quick, just a sidebar note, anytime you square a square root value, just a reminder, the square and the square root undo each other. Oops, let me get a different color. They undo each other. So that's why it's really easy without a calculator to know that the square of the square root of 113 is always going to be itself out from under the radical, no more square root sign. All right, let's take a look at example 4b. We know that 4 times square root of 95 is approximately 38.987, and then we have our other leg lengths of 15 and 36. So plug it into the formula and see if this is a right triangle. All right, this is not balanced on both sides, so it looks like it is not a right triangle. And just a really quick sidebar note, we've got 4 times square root of 95. So when you're thinking about these values and you're squaring a square root, remember the squared and the square root undo each other, but the 4 has to get squared as well. So the 4 squared becomes 16, and then the square of square root of 95 is 95, multiplied together to be 1520. All right, so then what happens when it's not balanced on both sides? Well, this takes us into the Pythagorean inequalities theorem. It states that for any triangle ABC where C is the length of the longest side, the following statements are true. So if C squared is less than the sum of A squared plus B squared, then you have an acute triangle. Implied statement shortens from the conditional statement. Our second statement, if C squared is greater than A squared plus B squared, then you have an obtuse triangle. And these might be easy to remember when you write C squared first and then the sum, because if C squared is bigger, it's obtuse, and obtuse is always the bigger sized angle. And then when C squared is first and it's less than the sum of A squared plus B squared, less is smaller, and acute usually is less than 90 degrees. So just an easy way to remember both of these statements. All right, so here's how you want to verify whether side lengths are a triangle, and then we want to classify it. So you always check to see if we even have a triangle to begin with before you are ready to classify. And if you'll recall from an earlier unit, we learned about the triangle inequality theorem, and it states any 2 sides must be greater than the third side. So it's really easy to see if this forms a triangle by selecting your 2 smallest values, so the shortest lengths, because if those 2 shortest lengths add up to be greater than the longest, it definitely forms a triangle. So we can see by this combination, 4.3 and 5.2 adds up to be 9.5. So our 2 smallest legs do come out to be greater than the longest leg, or longest side. So we know that we're dealing with a triangle. Next, we want to classify it. So this is where we use the C squared, either some unknown value, A squared plus B squared. So we don't know its relationship until we get to the end. So that's why we have blank between the 2 sides of the equation. So we know that 6.1 squared is 37.21, and then you square the other 2 values and add them together. So it looks like 37.21 is less than 45.33, therefore it is an acute triangle. All right, so if you need some refresher on simplifying radicals, then continue the video. If not, you can stop here and practice simplifying radicals on that extra sheet and bring your questions into class. All right, so simplifying radicals involves finding the largest perfect square. And here's a list of common perfect squares to be able to recognize without a calculator. So make sure you know at least numbers 1 through 25. So you want to make a list of all the factors of the number you're trying to simplify. And you want to find the largest perfect square. So I always start with 1 and itself, and then I continue the list, consecutive values after 1, until I find the largest perfect square. All right, so let's take a look at this example. We want to simplify square root of 128. Start by making your list of factors. Start with 1 and itself. And then I immediately see I go the next consecutive value after 1, which is 2, and 2 goes into 128 64 times. Boom, right there I see a perfect square. So I can stop right there, and this is the combination that I want to use underneath my radical that replaces 128. So we have 64 times 2, and we know that the square root of 64 is 8, so 8 will come outside of the radical. Since 2 is not perfect, it stays inside the radical. So square root of 128 simplifies to 8 square root of 2. OMG, bacon! All right, so that concludes our lesson for today. And bring your questions tomorrow, and we'll practice more Pythagorean theorem.